Hi.
Baby,
Hi.
how are you?
Good. How are you?
Good. So, when do you start back to school?
Thursday.
Okay. All right. So, I'm very, very tempted to start geometry with you, just to give you a little bit of a head start. But there's a couple of these things in algebra that I think it's important that we cover.
Okay.
So, I do believe we should start with, last time we covered this top one here, solving quadratic equations using square roots, completing the square and the quadratic formula. And granted, that was a big subject and we haven't really had time to review it, but I really want to make sure we cover the basis of algebra before you start geometry. And I think between today and tomorrow, we will be able to do that. If we miss this last section, that's not going to hurt you.
Okay.
But some of these other things might. So let's talk about properties of exponents. There's a few simple rules you need to remember. Example of this would be 2 to the third times 2 to the fourth is equal to what?
2 to the 7th.
Yeah. And you can do this as long as the bases are the same. In other words, if I said 2 to the third times 3 to the fourth, what's that? You have no idea, nor should you. In other words, the bases are different. So you cannot apply the rules of exponents. Okay? The number one rule of exponents is the bases have to be the same. And you know what I mean by the base, right? 2 is the base. So notice that whenever we're multiplying, we add the exponents. Now, let's look at this situation. There's really only 3 rules. What's that going to be equal to?
B, and then X minus Y.
Okay, good. An example of that might be 2 to the fifth divided by 2 to the third equals what?
2 to the 2nd.
Okay. That's rule number 2. Okay, this is rule number 1. That's rule number 2. And there's really only one more that's really important. And that's b to the x all to the y. What's that equal to?
I'm not sure.
It's b to the xy. In other words, if I had 2 to the third to the fourth, what's that equal to?
2 to the 12th.
Okay. Now notice what's going on in each case here. Here I am multiplying. What do I do with the exponents?
Add them.
One level less than multiplying. Here I'm dividing. What do I do to the exponents?
Subtract them.
One level less than division. And here I'm double exponentiating. What's one level less than double exponentiating?
Multiplying.
Okay, so that's what I do for that. And that's the way you remember these. In other words, you're never doing to the exponents what you're doing to the base. If you're multiplying the base, then you are never multiplying the exponents. Never make this mistake. 2 to the third times 2 to the fourth equals 2 to the 12th. That is not true. In other words, I am multiplying the base. Therefore, I cannot be multiplying the exponents. I have to be doing one level less. So it's really 2 to the 7th. Okay? And to me, that's the easiest way to remember it, is you're never doing the same thing to the exponents as you are to the base. And as long as you have the same base, then you just apply these three rules of exponents. Now, let me test you.
It would be 5 to the 8th. It would just be 6. It would be 3 to the 12th.
Perfect. All right. You understand that, I can tell. All right. And that's pretty much the properties of exponents. There are a couple of other things that you probably need to know. Let's talk about them. In other words, the three cases we just covered were same base, different exponents, right?
Mm-hmm.
Well, let's talk about different base, same exponents. What's that equal to?
I'm not sure.
It's A times B all to the third. In other
Okay.
words, if I'm multiplying different bases with the same exponent, then it's this. In other words, if I had 2 to the third times 3 to the third, what would that be equal to?
It would be 2 times 3
A
to
number.
the what?
Give me a number. What's 2 times 3?
Oh, 6 to the third.
Yeah. Okay. So that's really a different rule because that's different bases, same exponent. And it also covers division. In other words, if I have b to the fourth divided by a to the fourth, same exponent, different base, what's that going to be?
B divided by A to the fourth.
Yeah. And there's the 5 rules of exponents. That's it. You don't need to know any other 5 rules. The first 3, the base was the same, exponent was different. The last 2, the base is different, but the exponent's the same. Now, if I have this, different base, different exponent, have no idea what that is. You cannot simplify that. In other words, if I had 3 to the fourth divided by 5 to the sixth, cannot use any rules or properties of exponents to solve that. I just have to do the calculation. 3 to the fourth is 81. 5 to the sixth is who knows what. I don't know what it is. But the principle is we're working on properties of exponents, okay? It's not so much we come up with a number, it's that we come up with the proper application of the formula. All right, so we just covered that. Pretty good. Radicals and rational exponents. Hold on. Is that equal to? That's a perfect square number. You want to memorize your perfect square numbers.
Is it 8?
Okay. Yes. Now, tell me what your perfect square numbers are starting with 1. What's the next one? In other words, 1 squared equals 1. 2 squared equals, give me a, what's the next?
4.
What's the next one?
9.
Keep going.
16.
Keep going.
25.
Keep going.
36.
Keep going.
49.
Keep going.
64.
Keep going.
81.
And keep going.
100.
If you can memorize those, that is doing a lot. That will allow you to simplify most any radical. In other words, if I give you the radical of 200, you can see instantly that that's 100 times 2. And 100 is a perfect square number. So the secret is these perfect square numbers. You want to know what these are, always. You want to memorize them. Let's see, radicals and rational exponents. All right. That is true. The radical sign means the number raised to the 1/2 power. Okay? That's
Okay.
what a rational exponent is. In other words, sometimes, particularly when you get into higher mathematics, it's much more appropriate to use rational exponents. By that they mean fractional exponents instead of the radical sign. Because radical signs can be kind of strange. What's that mean?
Is it like a,
It means.
oh, got it.
So this case, there's kind of an implied 2. In most cases in mathematics, whenever anything is implied, it's 1. But with radical signs, it's an implied 2. In other words, when you see the square root of 4, there's an implied 2 there. And whatever that number is, that's what you put there. It's 1/2. And then when you get to cube roots or even fourth roots, you could write it like that. What's fourth root of 16?
16 to the 1/4.
Okay. What is that number? And if I told you it was a small whole number, what is it?
4.
Well, that would mean 4 times 4 times 4 times 4 is equal to 16. Is that true?
No.
Okay. So what number times itself 4 times is equal to 16?
2.
Yes. And And these things you want to know, okay? First of all, when they give you problems like 8 to the 1/3 or 16 to the 1/4, always know that your answer is a small whole number. It's either 2, 3, or 4. So think in terms of that. It's not 2.167898, okay? They don't give you that kind of problems in Algebra 1 or Algebra 2. When you see a big number like this to a fractional exponent, you can be almost certain that the answer is a whole number. Now, there is a rational exponent. First of all, rational means I can write it as a fraction. It's not square root of 2. It's not square root of 3. It's not pi. It's not e. It's 2/3. That's a fraction. That's the definition of rational. If something is rational, it can be written as a fraction. Now, how do I do this? What's the bottom mean?
What number 3 times is equal to 8?
Okay, good. What is that?
2.
Okay. So this is the same as 2 squared, which is?
4.
So 8 to the 2/3 power, always do the bottom first by taking the cube root of 8, which is 2, and then you square it. In other words, the numerator is the power you take it to, and the denominator is the root you take it to. Now, I could actually do these in either order. I could do 8 squared, which is 64, then I would have 64 to the 1/3. Cube root of 64 is also 4, so I get the same answer. I always do. But by doing the bottom first, you always simplify the problem, and you always keep your numbers smaller. That's the key to this one.
It would be
What's your first step?
what number 3 times itself?
Okay, yeah. Let's talk about that and call that the cube root of 27.
Okay.
That's what that means. In other words, we're going to take the cube root of 27, and that does indeed mean that what number multiplied by itself by 3 times equals 27. Well, what number is that? Especially if you know it's a whole small number. In other words, it's either 2, 3, or 4.
3.
Okay. So what's the answer here?
9.
Yeah. That's how you handle rational exponents. That's the root. That's the power. Let me think for a second. Here, let's see. Start at 1. Okay. Radicals and radical exponents. Let me just test you a little bit before we leave this. What's that equal to?
It would be 8 to the 1/3, which would be 2.
Correct. In other words, if you gave that as an answer, you would lose points because that can be simplified to 2. Okay?
Okay. Okay.
Now, what's that equal to?
-2?
Huh? Notice that -2 times -2 times -2, three negative signs together is going to equal a negative sign, and you're going to have -8. So that is exactly equal to that, and that is exactly equal to that. However, if I'm reluctant to write this way because I don't want to confuse you, but I'm going to anyway. If I take the square root of 4, it's actually plus or minus 2. Because +2 times +2 is equal to 4, and -2 times -2 is equal to 4. So when you take even roots, by even I mean this number right here, you always get a plus or minus answer. When you take odd roots, you either get a plus answer or a minus answer. You don't get either or. And as an example of that, let's take the fourth root of 16. That is going to be plus or minus 2. Because if I take plus 2, multiply it by itself 4 times, I get 16. If I take minus 2, multiply it by itself 4 times, I get plus 16. So when you take even roots, your answer always begins with plus or minus. When you take odd roots, it's either plus or minus, but not both. Identifying exponential functions. There is an exponential function. Hold on a moment. Let me think about this for a second, if that's really what they're talking about. No, they're not. Let me go back. Sorry.
It's okay.
Which of these is an exponential function?
The first one?
No. For something to be an exponential function, the variable has to be in the exponent. In this case, the variable x is on the algebra line. It's not in the exponent. The top one is an algebraic function. And we can always solve that by algebraic means. In other words, if I say 8 equals x cubed, take the cube root of both sides and I get x equal 2. Okay? So I can always take algebraic equations and solve them. When I have exponential functions, I can't solve that. If I said this, you have no way to solve for x. You could spend a year in your calculator and you would not solve for x. It's an exponential function. It's not an algebraic function. Much, much harder to solve for. Okay? It requires logarithms to actually solve for that, and then you even have to use your calculator. In other words, if you told me to manually solve that, I could spend a year, and if you didn't give me a calculator, I wouldn't be able to solve for it. because it's some fraction. In other words, obviously, x has to be between 1 and 2, right? Because 3 to the 1 is 3, 3 squared is 9. So the answer has to be some number between 1 and 2. And I don't know what it is. It's an irrational number. It might be 1.276945 and go on forever. That's the definition of irrational numbers, is they are basically decimals that don't repeat, and they go on forever, and you can't write them as a fraction. So there's quite a difference between exponential functions and algebraic functions. And the biggest difference is where the exponent is. Now, I noticed that it doesn't really require you, I don't see anywhere on here logarithms, although the next thing, exponential growth, solving exponential equations, and we might have to table that. But I don't think you're going to be required to know logarithms for your first exam when you take it to make sure you can continue on in geometry, which is what our goal is. Let me write some equations here, and I want you to tell me which ones are exponential and which ones are algebraic.
The first one is algebraic and the second one is exponential.
Very good. And we're not even going to talk about solving these. That it doesn't require that. It's just talking about identifying exponential functions. So an exponential function is merely a function that has the variable in the exponent. Okay? If I said this, that's an exponential function. Even though my variable is both on the algebra line and in the exponent, that is still an exponential function. Exponential growth and decay. This is actually a pretty big subject. There's actually three major equations for growth and decay, but I don't think for Algebra 1 they need you to know all three. This is the primary one. That is the exponential growth function. Let's say that you took $100 and put it into a bank account, and they're going to pay you 4% per year for 5 years. What is your bank account going to be worth at the end of 5 years? Well, let's say 0. You took $100.
So it's $100.
That's what that is. Whatever your initial amount is. R is your annual interest rate. I think I said that was 4%.
So 0.04.
Well, it was 4%, but you do always want to turn that into a decimal. So you're correct. It's 0.04. I never put that leading zero there. It's completely unnecessary. I don't know why they teach all my students do it. To me, it's a waste of breath. In other words, that number is the same as that number. If I put a 0 there, does not matter. No need for me to express that that is 0.
Yeah.
So all I need to know is after the decimal point. As long as the number before the decimal point is not 1, 2, 3, or 4. If it's 0, you do not need to write it. In other words, this is another case where it's kind of implied. And what was t?
5.
Okay. So what we have, y, which is the amount your bank account will be worth, is 100 times 1 plus 0.04 to the 5th power. That's a number you get out of your calculator. In other words, they don't ever expect you to do this manually. Okay? But you do need to know how to do this in your calculator. You got a calculator yet?
Nope.
When are you going to get one?
Uh,
What's their requirement? What's the school's requirement?
the school's requirement is that we're supposed to go to school first and then find out exactly what we need from every teacher and then you get school supplies.
That's fine. Yeah, I will not get ahead of that. If that's, yeah. Well, let me just tell you that the only way to get that number is to put it into a calculator. And usually it needs to be like a graphing calculator. It needs to be one of the better. In other words, you're not going to put that into one of these tiny little calculators that you get on your phone sometimes. But you can come up with a number there. And that is precisely what your $100 would be worth at the end of 5 years. So the higher that R is, the better off you're going to be. The longer you leave it in there, the higher T is, the better off you're going to be. And the more you put in, the better off you're going to be. This is annual compound interest. Now, there are actually 3 kinds, but I'm going to kind of gamble and think that the only one they expect you to know is the first kind, which is this one. So if you're looking to memorize something, memorize this and know what each of those letters mean. Know what Y is, know what A sub 0 is, know what R is, and know what T is. It's called A sub 0 because it's the initial. Whatever you start with. You might start with $1,500. You might start with $1,517. Does not matter. Whatever you deposit, you do this interest rate, and for that many years, and you can calculate what it's going to be worth. And that's a very common bank return. If you go to a bank, they're very likely to pay you based on this formula. In other words, they're going to pay you annual compounding interest. There are a couple of others. There's annual, there's greater than annual, where they would compound it every month or maybe even every day. And then there's continuous compounding. The real world is really more continuous compounding. And I'm not going to go into it because it gets more complex and don't think you need to know it to start geometry. It doesn't come up in geometry. But they are certainly possibly liable to ask you about annual compounding. Now, what's the difference between growth and decay? Growth, well, if you go put money with a bank, it grows, right?
Mm-hmm.
What kind of thing decays? Give me an example in the real world of something that decays, which means it loses value every year. Can you think of anything?
No.
How about the value of a car?
Okay.
Okay. In other words, if you go out and buy a car for $20,000, guess what? Every single year you own it, it's going to decrease in value. Let's say it decreased by minus 5%. Okay, so 5% of 20,000 is 1,000. At the end of 1 year, it would only be worth 19,000. That's decay. And it's exponential decay. Okay, it's not linear, it's not algebraic decay, it's exponential decay. Other things that decay, how about uranium? Uranium loses a certain amount of its mass every year until it basically disappears into nothing. All radioactive substances do that. They all experience radioactive decay. And the reason it's so dangerous when an atomic bomb goes off somewhere is that most of the substance that's in the area is plutonium, which takes 26,000 years to lose half of its material. Well, that makes wherever the bomb goes off uninhabitable for 26,000 years, because 26,000 years later, there's still half of the original radioactive material, which is poisonous to humans, in the area. And 26,000 years after that, there would still be a quarter of it left. So a lot of radioactive substances have very, very slow decay periods. And that's why nuclear weapons are so dangerous, because when they go off, whatever the area is they cover with their radioactive material, it becomes uninhabitable for thousands and thousands and thousands of years, which obviously doesn't work well for the human species. Let's hope North Korea doesn't become that.
Mm-hmm.
Although I fear that it will. I think North Korea may end up being the first uninhabitable zone on the planet.
Well, isn't there one, there's some part of Germany, I'm pretty sure that you can.
Germany, but Chernobyl.
Yeah, Chernobyl.
Yeah, which is in one of the one of the old Soviet republics. Not sure which one, but yeah, they had an accident. They were at a nuclear power plant and they had an accident and it released all these radioactive materials into the atmosphere, and it has basically made Chernobyl uninhabitable. The difference is Chernobyl is maybe 20 square miles. It's not big.
Yeah.
If a nuclear war starts in North Korea, the entire peninsula of North Korea will be uninhabitable for 50 to 100,000 years.
Yeah, that's not good.
No, not at all. And at this point in human history, Chernobyl is probably the worst case. even 3 Mile Island in the United States, we had an accident at that nuclear power plant. And that made, it wasn't as bad as Chernobyl, but same principle. In other words, nuclear power is great. It's totally clean, except it really isn't. If there's any accidents, it destroys the area for 100,000 years. Well, it's not exactly what you would call clean energy. So
Yeah.
I'm not sure nuclear power is the solution for our global warming or our climate change problem. All right, let's go on before I get into politics. Okay, so we've talked about exponential growth and decay. Exponential growth, another case of exponential growth would be bacteria in a petri dish. Okay, let's say I started with 100 bacteria in a petri dish. Well, bacteria always grow exponentially. I might end up with 10,000 bacteria within 2 hours. That's how fast they grow. They might double every 8 seconds. Okay, so the reason this is such an important subject in math is because so many things in our real world have either exponential growth or exponential decay. And in fact, most everything does. The one example I pointed out to you, which was a bank account, that's artificial. That's not in the real world. That's a bank coming up with a special rule. Okay? If you look to the real world, everything either grows with continuous compounding or continuous decay. And that's eventually what you have to learn are the formulas for continuous growth and continuous decay. But that comes more in Algebra 2. All right, let's see here. Solving exponential equations. Hold on a second, I gotta think for a moment. Wow. Let's solve easy ones. First of all, it's an exponential equation. What does that mean? Variable has to be where?
In the exponent.
Okay. Here's an exponential equation. Variables in the exponent, what's x equal to?
4.
2 times 2 times 2 times 2 would be what?
Wait, then, okay. Hold on.
In other words, whatever answer you come up with and give me, check it out. It's not 4. 2 times 2 times 2 times 2 is 16. So what's our answer?
3.
And 2 times 2 times 2 is 8. So there's an exponential equation that we can solve relatively easy. And I'm pretty convinced that in Algebra 1, you're only going to have to solve the easy ones. In other words, the more difficult ones, if I told you this, that's not so easy. Now you got to bring in logarithms, and they don't mention the word logarithm anywhere on this page. So I know they don't want you to necessarily be able to do these. The ones they want you to do are ones like this. In other words, always where the answer is a small whole number.
Just
Know,
3.
know that. What is it?
3.
What's that?
4.
2 to the 4th is
64.
no.
So
Let's go through the 2's because this is actually pretty important. 2 to the 1st is 2. 2 squared is 4. 2 cubed is what?
8
2 to the 4th
is 16
2 to the 5th.
is 32.
You should actually have all of these memorized. Powers of 2 are extremely important. It's what our entire computers are based on, is a binary system. So knowing what 2 to a certain power is pretty important. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. And 2 to the 10th is 1024. Now, when computers were just being invented, you had 16K. Next increment, they went to 32K. Next increment, they went to 64, and then 128, and then 256, and then 512. Finally, that was 1 megabyte. So these numbers are very important in the way life develops, especially computers, because they're binary. So you kind of want to know your powers of 2. And the one, I memorized the 5 on the left. I can tell you those by heart. And the other one I know is that 2 to the 10th is just about 1,000. With me?
Mm-hmm.
So if 2 to the 10th is 1,000, what's 2 to the 20th?
10,000.
Well, that would be what? 2 to the 10th times 2 to the 10th, right? Add the exponents, same base, add the exponents, that's equal to 2 to the 20th. Excuse me, 2 to the 20th. Okay, what's 2 to the 10th? I said it was about 1,000. It's actually 1,024, but I'm going to round it off. What's 1,000 times 1,000?
10,000.
No. Add the zeros. How many total zeros do you have?
6.
It's 1 million. So, if I'm memorizing these, I know that 2 to the 10th is 1,000. 2 to the 20th is 1,000,000. 2 to the 30th is about 1,000,000,000. Have you ever heard the story of the checkerboard that has 64 squares on it?
No.
And the guy wins a contest to marry the farmer's or the king's daughter. And the king says, okay, what do you want? I'll give you anything. And the guy says, I want 1 grain of rice on the square number 1 of a checkerboard. And then I want 2 on square number 2, and I want 4, 8, 16, and so forth. Well, you can tell by this that by the time he got, there's 64 squares on a checkerboard. By the time he got to the 30th square, he was entitled to 1 billion grains of rice. Okay? 2 to the 40th is 1 trillion. That's probably more rice than exists in the world. 2 to the 50th is 1 quadrillion. That's, now you're getting up to the number of sand particles in the earth. 2 to the 60th, by the time he got to the final square, 2 to the 64th, it was a number that was bigger than the molecules in the universe. So that's the power of 2. When you start doubling stuff, it grows very, very fast. And that's actually a really interesting story. I mean, it really is, because it illustrates that the king had no concept that if he kept taking 2 to additional powers, he would get to numbers that exceeded not only his kingdom, but the entire planet. So a good one to kind of always remember is 2 to the 10th is about 1,000. And then you can do higher powers of 2. Now, if you wanted exact numbers, you'd have to feed these into a calculator. But we're not looking for exact numbers at this point. Solving exponential equations. Okay. How about this? How do I solve that for x? Hold on. Sorry. Not an exponential equation. No, we've covered. Let's solve it anyway. It's not an exponential equation. You see why?
Yeah,
because the variable is not in the exponent. However, so this is an algebraic equation. Well, you still need to be able to solve algebraic equations. How do I solve that? What do I have to do to both sides?
divide by 2? No.
You're trying to get an answer that looks like this. So you got to get rid of that 1/3 exponent. How do I get rid of that 1/3 exponent?
Multiply by 3.
Not multiply, exponentiate by 3.
Okay.
See the difference?
Yeah.
Multiplication would be if I stuck that 3 down in front of the x. Exponentiation works because what is this now equal to?
X.
Just x to the 1, right?
Mm-hmm.
Okay, and what's 2 to the 3rd equal to?
8.
There's your answer. So even though that's an algebraic equation, you still need to be able to solve for it. And you basically solve for it by making that exponent equal 1. Let me give you a slightly harder one. How would I solve that? What would I have to exponentiate both sides to?
1/3 maybe?
If I exponentiate the right to 1/3, then that becomes 2/9. Remember, I'm multiplying these two numbers. And I want it to become 1. So what do I have to multiply the right side by in order to get x?
2/3.
No, if I multiply by 2/3, that becomes 4/9.
Oh, 6.
No? Shoot. I didn't mean to do that. 2 equals x to the 2/3 if I exponentiate it by 3/2. Hold on one second. Hello? Sorry about that, Phoebe. Okay, so when you have a fractional exponent like this, if you take it to the reciprocal, then notice that 2/3 times 3/2 is 1.
Got it.
Okay, so this is actually, I haven't written this correctly. That's the original. 2 equals x to the 2/3. So therefore, x equals 2 to the 3/2. In other words, here's what I'm going to do. I'm going to take this to the 3/2, and I'm going to take this to the 3/2. Those two cancel out, leaving x. And what I have on this side is what? What's 2 to the 3/2? First of all, you can't take the square root of 2. Gives you an irrational number. So do the numerator first. What's 2 cubed?
8.
So it's the square root of 8. That's the answer. And then that actually reduces to 2 root 2. Okay? So you don't always get small, perfectly whole numbers, although you will when you take this test. In other words, until you get to Algebra 2, you're always going to have whole numbers.
Okay.
Okay? So, I think we've covered every topic here except that bottom one. Arithmetic and geometric sequences. That is a really big topic. Let's have a look at what else we have here to look at. Because you really only have one more session, correct? Before you start back to school, essentially?
Yeah.
Okay, so we've got to cover that. Can probably do a simple version of that in a half an hour. We can certainly do that in 5 minutes. This, we've already done that, but that's a big topic. We did that like 5 or 6 sessions ago. This, real easy. This, real easy. So we've got this much material to cover and one session left. So I'll try to do an adequate job of that. And I will put emphasis on what I think you're going to be tested on.
Okay.
Okay? So, Phoebe, I will talk to you tomorrow at 11, correct?
Yes.
Talk to you then.
Yep, sounds good.
Bye-bye.
Bye.